Good day. I'm Bogdan Stefanescu from the Technical University of Civil Engineering, Bucharest, and I will present you a few ideas about seismic torsional effects on construction. Then I'll speak about the structures and the loading schemes that we used. Then a few words about the results that we got, finally some conclusions and acknowledgements. The torsional effects occur on structure even in the case of symmetrical ones. Seismic design codes usually consider an additional eccentricity of about 5% to model this torsion. When considering the variable loads that come when computing the mass, a certain fraction is considered, and this fraction is considered to be uniformly distributed on the floor. What happens if this variable load is not uniformly distributed on the floor? That is what we try to investigate in this paper. So we considered two structures having the same floor plan, one with 7 stories, another one with 20 stories. The spans and the base are about 8 meters, and the height of the floor is 3.7 meters. The braced frames, the eccentrically braced frames, are placed on the side frames, and for the structure with 7 stories, we have this scheme, and this one for the structure with 20 stories, having also some outrigger system. So pseudo-real possible most unfavorable loading situations were considered, starting from the fraction of the variable that is used for determining the mass. In this case, it's 0.3 for office buildings, and we consider this load to be agglomerated on one side in the most unfavorable position, with the maximum factor of 1.5, which corresponds to the persistent design situations where that variable load has the dominant effect. Under these circumstances, we got 5 schemes for loading. One is centric, which was used for reference. Then eccentric, which is in fact what it is used in seismic design codes with an eccentricity of 5%. Then XN03, this is another loading situation coming from the codes, which consider the seismic force on one main direction of the building and 30% of the seismic force on the other main direction of the building. Finally, we took the two loading schemes that we considered. So the variable loads agglomerated on the longitudinal side and on the transversal side. Using these schemes, we analyzed the two structures, so we got a great amount of data. That is why in this paper we focused only on the braces in compression, the links, and the columns in compression because of the action of the seismic force. So we looked at the compression force in the braces and in the columns, and the shear force in the links. Obviously, we looked on the most loaded structural members, that is groups 1 and 3 on this image, where the torsion effect is more important than in the groups 2 and 4. All references are made to the centric situation, which is considered to be 100%. So let's look now at some results that we got. For the 7-story buildings, we notice an increase of 8–9% when considering the torsion effects, and an increase of up to 17% when considering the agglomerated situation, the effect increasing at the top floors. If we look now on the longitudinal direction, we see that the influences are smaller, but keep remaining the same trend. Now we'll have a look at the links. Again, in the design approach, we have a a 9–10% contribution of torsion, and when agglomerating variable loads, we can go up to 13% in the top floors. Similarly, for the longitudinal direction, but with smaller values. And what we could notice till now, and we keep on noticing, is that Xan 03, that is considering the 30% action on the normal direction, doesn't bring much. If we look now at the columns, we see again that the contribution of torsion is below 6–7%. However, if we look at the agglomerated loading situation, we can see increase of 30–40% in the top floors, considering the fact that here the loads are smaller and the cross sections are smaller, so the changes become more important. Similarly, on the longitudinal direction with a little smaller values. So if we try to summarize some conclusions for the 7-story building, we can notice that the torsional effects are more significant when speaking about the short direction, and agglomerated distribution generates larger values than what the code torsion, let's say, brings. The major differences being in the columns at the top floors. Again, we could notice that introducing that 30% force normally to the main direction of the seismic load does not bring anything important. Now, if we move to the 20-story building, we considered here the results in the most representative 10 stories, so 2 from the ground floor, 3 around each outrigger zone, and 2 from the floors. We use the same approach, that is, we look at the influence of torsion in eccentric, so we see that it is around 9–10%. And on the agglomerated load, what you can note here is that around the outrigger systems we have major increases up to 46% in the compressed diagonals. We move now to the longitudinal direction for the diagonals, and we see the same idea, that is increases but smaller than for the shorter direction, with concentrated increases in the outrigger part. Moving to the shear forces in the links, the trend remains up to 10% for seismic design code approach, and around 40% in the neighborhood of the top outrigger system. Again, on the longitudinal direction, smaller values, and similar for the compression forces in the columns, with increase of values in the neighborhood of the outrigger systems up to 30%. And with a little smaller values on the longitudinal direction. So if we try to summarize some conclusions for the 20-story building, we can see that the effect on the short direction of the building remains more important in this case too. Then the agglomerated distributions that we imagine give values that are larger to the code approach, and again the 30% approach doesn't bring much. So if we move now to conclusions, we could notice that the effects of general seismic torsion are more important on the short direction of the building than the approach that is used in codes, in present-day codes, of 5% is, for the eccentricity, is reasonable for this case, for instance, where we discussed about an office building, but it would be different if we are speaking about an industrial building where the ratio between the variable loads and self-weights are different. Then variation of internal forces with the floor level are expected to be significantly less smooth if we have an outrigger system. There we noticed some important changes. And finally, using the 30% force on the normal direction doesn't lead to important changes in the case of brace systems. Express our gratitude to Professor Peter Knödel from Karlsruhe Institute of Technology for the very fruitful and useful discussions that we had. And thank you for listening.